All right, great. Well, thank you for attending our lecture again. Monday lectures it's going to be two things we're going to discuss today. One is on the coming exam on Thursday, and the other is about this shear we're going to get into. Okay, so before we talk about shear, I just want to talk about exam real quick. Made a problem over the weekends. I will discuss with Dr. Sneed and finalize it either later today or tomorrow. So, excuse me. So in looking back at the problem, I have in mind, it's going to be three problems. First problem is going to be multiple choices, and the second and third is going to be calculation problems, full solution problems. So the exam is designed to have to give you guys an hour, approximately an hour to finish. Excuse me. So it's not that hard, but we give you 3 hours on Thursday from 1 to 4, so you should have enough time. I know several students have accommodation letters. Given that you will have twice amount of time for the exam, so I think that should address that. If you still have issues or questions, feel free to email me or let me know so we can talk about it. Now, in terms of exam coverage, and it's going to be chapter 1 to 3. I talked about this already from last lectures. And for the multiple choices and including a little bit detailing and singly reinforced cases, maybe doubly reinforced analysis concept in the first problem. And the second and third is going to be calculations, at least one analysis problem, one design problem, right? So in terms of analysis, you can think of it, it's going to cover the singular reinforced section analysis and doubly reinforced section analysis. And for the design, it's going to be mainly for singular reinforced section design, okay? Now think about for the design, right? There are two things we talk about in design. A design with given geometry, that is sections given. All you have to do is design reinforcement. And second type is actually design a section without known geometries, without given sections. That means you have to determine the height, the width of the section, and then proceed going from there. Okay, so both problem will be covered. Which one you find out on the exam date. Okay, now specifically about the exam, it's going to happen Thursday from 1 to 4 o'clock. You have 3 hours, but don't kind of utilize the full 3 hours for your work. Save your time, save yourself some time. We're talking about like 10 minutes or 15 minutes just to have enough time to scan your work and upload it to Canvas. Okay, so don't forget about that. Now I have seen some students forgot uploading their homework and due the last minute and email me about what to do. And my answer is always going to be like this: we already set the automatic deadline, so if you miss, you're really at the mercy of the graders. Okay, of course I can do something about it, but I like to keep it how to say this, constant or universal across the board, so we have a fair game here. Okay, all right, so that's as much as about the exam. Do you have any question right now about the exam, guys? Any questions for me on the exam, content, format, any other things you have? Dead silent. Okay, all right. Okay, so I hope you're ready. That means I don't have to worry too much about it. And two finer things I just want to address today that, as I said maybe before recording, I noticed that some of us getting a little bit lag behind. Maybe it's just middle of semester, we'll get tired and weary. If you have trouble submitting homework on time, I suggest you talk to me and maybe we can figure out a plan. Because I do see students have very few students started to be delayed in the homework submission or just totally dropped it. I want you to know that if you continue this fashion, we might have a problem, right? We might have a problem. So take a look at your homework grade. If it's degrading, if it's somehow you couldn't submit it on time, you need to talk to me, okay? I started reaching out, but I want you guys to maybe volunteer to talk to me so we can have a better tailored plan for you to improve, okay? So that's about that. And the other final thing is that about practice, okay? Now, don't wait till the last minute to do your homework. I know there are a lot of courses you're doing right now. Some of them online can be tiresome, but reinforced concrete design class is really about practice. we redesigned the homework this semester just because we want to give you guys more practice. So do start your homework early and ask me questions. Okay. Now I have a few good students always ask me questions. I can see their homework grade reflect that. And I surely hope that the first exam grade will also reflect that. But for the rest of us, please send me any email or just ask me any questions. Okay. Now, my schedule sometimes can be a little bit ad hoc because this semester everything's online. But if you send me email, I will sure respond and we will definitely schedule time. Okay. Now I have 1 or 2 instances that I email back the students asking about a favorite time I didn't get back. Maybe got lost in the communication. So if you haven't heard back from me, I will never do this, right? If you haven't heard back from me, that means, just bug me again. I will definitely respond and you will get help. Okay. Don't just lay it down like that. Okay. All right. So that's about it. So let's continue to talk about shear. All right, I will have a review session on Wednesday for the exam. Okay, but today I'm just going to talk about shear. Okay, so let's march on and finish this part of the lecture. Okay, so let me share my screen. Excuse me, let me share my screen here. Good. Okay, so shear, right? We talked about the shear in concept last time. All right, so quick recall what we did last time, right? So we show you a beam, right? It's a simply supported beam like this. And we also show the stress distribution. Remember, stress distribution, we show 3 elements. Now divided by the neutral axis, have an element on the top, compression zone, element in neutral, element at the bottom, C tension. Okay, and we also showed you that if you flip it, right? If you flip it, they have a certain element orientations, right? Element
Bob, I don't
orientations.
think we're seeing what you're drawing.
Anything? Okay, let me see here. Something
There it
wrong with
goes.
my. Can you see it now or?
Yeah, I can.
Okay, good deal. Thanks. Just slow internet, I guess. So if I draw the principal stress directions, you see some of the stress trajectories. And we talked about this. We have diagonal cracks. We have diagonal cracks, okay, on the side, and we have flexure cracks in the middle, of the section, right? And now we designed previously mainly on the longitudinal reinforcement. This is called a longitudinal reinforcement. Longitudinal reinforcement. Okay. And these are taking care of the flexure cracks. These are taking care of the flexure cracks. Okay. We also talk about we're going to design a transverse reinforcement, vertical transverse reinforcement. And these will take care of the shear. So we'll take care of the diagonal crack. We'll take care of the diagonal cracks. All right. So that is the design concept. That is the design concept. So we basically have longitudinal bars for bending and vertical bars for shear. Vertical bars for shear. Okay. Now, but the ultimate question is, why do we need the vertical bars to begin with? Why do we need the vertical bars to begin with? Okay, so today we're going to take a look at it, the reason or mechanism, right? So lecture 12, shear stress transfer mechanism. Okay, and then the objective is to understand the shear transfer, right? Shear transfer mechanism. Okay, and to take a look at the shear transfer mechanism, let's pick a corner of the section here. I'm just gonna draw a blue line here. So I'm gonna take a look at this corner here, okay, and then do a free body diagram. So maybe let me zoom in a little bit. Okay, and this is my corner of the section. And now look, I have a diagonal crack here, right? I have a diagonal crack here. So I am going to expose that diagonal crack by cutting it like that. Okay, by cutting it like that. cutting it like that. Okay, and naturally I'll have a leftover part, the right hand side, right, to match at this diagonal crack. Okay, and this is my support on the left. This is the support on the left. So for a free body diagram, right, I want to do a force decomposition, see what kind of internal forces I have on the cut, right? So naturally I have a compression force here, I call it C1, okay? So this compression force also is accompanied by a shear force Cy, Vcy here, okay? And in parallel, almost in parallel of this diagonal crack, I have a parallel shear resistance force called VA, okay? And then on the bar, at the bottom section here, I have a rebar here, right? I have a rebar sticking out, and these are my bar, right? These are my bar, right? On the bar, I will have a so-called Dow reaction, Dow shear. That is shear by the reinforcement, in the longitudinal reinforcement. And I also have tension caused on the bar as well, T2, right? So on the other side of the crack, I will have equal but opposite tension from the bar. I have a Dow reaction equal and opposite here, okay? And also have the inclined crack, right? Inclined crack, there's a shear resistance. Let's call it VA here. Okay, let me finish the bar. Okay, all right. So let me start naming them, right? So I say that, okay, based on this diagram, shear, stress can be transferred across the diagonal crack, okay, through the following ways. One is VCY, right? VCY, this one here. And that is the shear in uncracked compressive zone. Shear in the uncracked compressive zone. Why is that, right? Why is this is the uncracked compressive zone? Because the diagonal crack, notice here, my drawing is a little bit inaccurate. The diagonal crack only happened here, where on the very top, this right here, it does not have a crack anymore. So that is from the cut, right? That is from the cut. I cut it that way, right? So in this region, I still have shear resistance, but that's from the uncracked section. A little bit part that's still connecting the two parts of the beam, okay? And I also have VA, okay, in parallel with the diagonal crack, VA in parallel with the diagonal crack. And this is called interface, shear transfer. Okay, or better known as aggregate interlock. Okay, so what's really happening is if I zoom in to see this, right? If I zoom in to see this right here, right? So I have a diagonal crack, but on the crack surface, I will have a roughened surface due to aggregates. These small circles, these are aggregates. Okay, so these are the section. I shouldn't cut like this. These are the top surface, and bottom here, there's another surface right here. You can see it. So these aggregates kind of bite into each other, right? So this is called aggregate interlock. Provide the shear through this aggregate interlock. And last but not least is so-called the Dow reaction. The Dow, D-O-W-E-L. The Dow reaction. Okay, Dow, sorry. Let me see, Dow action. Okay, Dowel action. Okay, but this Dowel action is coming from the longitudinal reinforcement. Okay. All right. So as you can see that if I don't have a transverse reinforcement, if I don't have stirrups, no vertical bars, right? My total shear resistance come from the aggregate interlocking, shear from the compressive zone, and the Dowel reaction. The Dowel reaction. Okay. So the key here is right now we can call this, right? We can call all this, right, as VC. Okay, so that means this is the shear resistance from concrete. Okay, so shear resistance from concrete. That means all these three mechanisms constitutes the shear resistance from concrete alone. So that is to say, if my shear force applied to the section is smaller than the shear resistance can be provided by the concrete, I'm safe. Isn't it? So that is the shear resistance from concrete. Okay, all right. But what if, right? What if V applied VU? Remember, this is factor shear, right? Factor shear. What if VU is greater and bigger than VBC? Okay, and this is strength reduction factor for shear. Strength reduction factor for shear. Okay, right? So if the applied shear is bigger than the design shear, right? Well, what will happen, right? So we'll say in this case, web reinforcement or shear reinforcement needed. Web reinforcement is needed. Okay, so what happens after we introduce the web reinforcement? Okay, so we still draw a section as a comparison, right? So let me draw this section right here as we drew before, and this is on the left is the section without stirrups, right? Section without stirrups. So as we shown before, have the compression in the compressive zone, shear force VCY, okay, and I have VA, shear interlock, aggregate interlock, right? VA here, and this is T2, Dowel reaction as well, VD, and here T2 from the bars, and Dowel reaction, Dowel reaction here.
Yeah, I already did it.
Okay, and then the bar is right here.
Interesting, it was actually in person.
Okay, bar right here.
Engineering up in St. Louis.
Let me get this one here.
It's like site development. So hopefully.
Okay, so that's the bar, right? That's the bar. Okay, and this is the case
like
without the steel, right? This is the case without the steel.
If I do move forward, I'd be
right?
talking
What
to
if I have a case
people I
with
could go up
steel,
to their
right?
office to
And I
talk to,
can
like,
take
the
a look
vice
at
president
here,
and different departments.
right here.
So hopefully
and
that means
then
something. Because he took the time
instead
to
of the original section that I don't have any stirrups, right? Instead of the original section that I don't have any stirrups, I now have vertical bars. I have vertical bars, right? So let's draw the vertical bars here. Well, let me cut this portion out. Okay, so this will be all the way down here, all the way down here. Okay, and then I have a handlebar on top as a compressor reinforcement and a tension bar at the bottom right here. Okay, so before I have a support on the left, and this is my support on the left. Okay, and again, the Dowel reaction is still there. So this is VD, this is T2. Okay, this is T2, and this is VD. Okay, now my so-called aggregate interlock still here, VA. Okay, again, the compression's there as well. Shear, VCY, still there as well, right? What's added, what's new is this reinforcement here, that these arrows provided VS. That is shear from the web reinforcement. That is shear from web reinforcement. Okay, now this is a side view, right? This is side view. What does it look like in the cross section, right? What does it look like in the cross section? So in the cross section, you see that usually we draw a cross section like this. We have the top bars, have the bottom bars, and we show the stirrups like this. Stirrups like this. Okay, and for T-beam, for T-beam, we have our stirrups. Same thing, right? Hanger bar here, tension bar here, and stirrups like this. Okay. Now, quick question here, right? So I have stirrups like this, right? Stirrups like this. Peter, are you there?
Yeah,
Hey, how are you, buddy?
pretty good. How about you?
Not too bad. So here, so I draw the cross-section view, right? I have two legs of stirrups, okay? So when I calculate the area of stirrups here, right? Will this cross-section here include two legs or one leg?
Hang on. Are you pointing to the right side?
Well, the top view, can you see this one here? This is the side view, right?
The screen's going kind of choppy. Are you okay? The right.
So what I'm asking is, when I cut here, right? Do you see this blue line here?
Yeah.
Okay, the blue vertical line. So if I were ask you to find out the area of steel in this blue line cut, right? Would this be one leg or two leg of stirrups?
I would say two.
Two, right? That's correct answer, right? So what I'm having you here, if I have a stirrups like this, additional bars like that. How many legs do you have right now?
4.
4, right? So that's correct answer. So all based on what type of stirrups you have. All based on what type of stirrups you have. Okay, so be careful on the calculation of stirrups area, right? So we usually call it, let me use the here. We usually call this ASV, shear, okay? V for shear, okay? So that depends on how many legs, right? Depends on number of legs in stirrups. Now, we don't have to worry about right now, but later you realize if we say number 3 stirrups, right? You use ASV equal to 2 multiplied by the number 3 area. Okay, so a little bit detail here. Okay, all right, so that's about it. That's how we're going to reinforce the section for shear. Essentially, we're gonna say that total shear now with this reinforcement, V total, have two components. One is called concrete VC, and the other is from the steel VS. Okay, now further VC should equal to VA, the aggregate interlock, the shear from the compressive zone, and the Dow reaction. But normally we all lump them together, use one term. We don't have to differentiate them. Okay, we don't have to differentiate them. All right, so this is the shear stress transfer mechanism, shear stress transfer mechanism. Okay, all right, now let's continue. Let's continue, get into a little bit lecture 13. I'm going to do review, so running a little bit fast today. So 13 is design for shear. Okay, design for shear. Now objective, right? Learn design equation for shear. Okay, all right. So we have gone over the basic concept of how shear transfer across the crack, across the crack. So we want to get into the design part. So recall first how we design for moment, right? How we design for moment. So phi mn is the design moment, has to be greater or equal to mu, which is applied. Remember? And we have to determine a phi, which is a stress reduction factor, that is either 0.65, 0.9, or some equation in terms epsilon t, right? The tensile strength of the concrete, sorry, of the steel in the concrete, right? The bottom layer, right? That's how we design for flexure. However, for shear is a little bit different, right? It's a little bit different. So for shear, phi Vn, okay, phi Vn, that is design shear resistance, has to be greater or equal than Vu. Okay, but now the phi stress reduction factor is a constant, is 0.75 for shear. Okay, and you can find this in the code in ACI, design equation wise, it's 9.5.1.1, and for the stress reduction factor for shears, 2.1.2. Okay, and we further say that the resistance Vn or slash V total shear resistance come from two parts. One's from concrete, Vc, okay, the other from the steel. All right, so this is from concrete, and this is from steel. Okay, and you can find this equation at ACI 22.5.1.1. 22.5.1.1. Okay, all right. So things become a little bit easier, right? How do I design for shear then, right? How do I design for shear? So I will give a VU, okay? I'll divide it by phi to get a Vn. And if I want to find out how much shear for the stirrups, for the steel, I just use this equation right here. This equation right here. Okay, but we still don't know what is the shear resistance from concrete, right? We all know that shear resistance from concrete from previously has three components. That's VCY, VA, and VD. But that's too complicated. That's too complicated, right? So basically ACI says, look, ACI says, look, without axial compressive reinforcement, or without axial compression, we see, use black color still, we see equal to n 2 lambda square root f prime c b w d. Okay, that is the simplified format for concrete shear resistance. Okay, and you can find this from ACI 22.5.5.1. All right, so this is the shear resistance from concrete. So explain a little bit, right? What does each parameter mean? So lambda here is the normal weight or lightweight factor. Okay, now lambda equal to 1 if it's normal weight, lambda equal to 0.75 if it's lightweight. Okay, lightweight. Okay, for now we can use 1, right? We can use 1 always, right? F prime C is the concrete compressive strength. Concrete compressive strength. Okay, and BW is the width of the web. It's the width of the web. All right, be careful here. Now, if the section is a rectangular, then BW is essentially just the width. So BW equal to B. But if the section is a T-shape, then this is BW right here. Okay, what if I have I-beam? Then the I-beam BW is right here. Okay, all right. So you can think of it, BW is almost the narrowest, right? Narrowest width across the section, Okay, now D, which is the depth of the beam, right? We all know that already. Depth of the beam. Okay, but when D when depth is not prescribed, we can estimate that. We can estimate that equal to 0.8 H. Okay, 0.8 H. So this is the compression. Sorry, this is the shear for the beam without compression.
Does F prime C have to be in PSI for this as well?
Yeah, so square root of prime C, right, always has to be in PSI, right? So whenever you see a square root of prime C, it always in PSI. Let me just note here. Okay, got it? All right, good deal. Okay, so this is the compression from the concrete. This is the, sorry, this is the shear from the concrete. Okay, now we know this already, right? And now let's talk about the shear resistance from steel, right? So shear from steel. Now this is a little bit tricky. This is a little tricky, right? So as we've seen before, there are two legs of stirrups taking care of that side view, right? Taking care of that side view, right? So let me just draw a side view drawing again. Side view drawing again, okay? So let me do this. I have a cross section, and this is the cut, diagonal correct. And then I have stirrups. So I'm just going to use dash line here, dash line here, dash line here, stick out, dash line here, stick out. And I have my longitudinal bars go here. Okay. Now these stirrups, right? Let me just draw another bar here. These stirrups, right, will provide a tension to help stitch the crack. Okay. Now assume the spacing between the vertical stirrups is S here. Assume the spacing between the stirrups is S here, okay? And that's the support here. And now let me make some assumption now, okay? Let me make some assumption now. I will assume, right? The diagonal crack, I will assume the diagonal crack have an approximate angle of 45 degree here. How so, right? How so, right? Where is 45 coming from? That is, I assume the depth, which is right here, depth, okay, equal to the length of the diagonal crack. Okay, so that's why it's 45 degree. This is assumption, by the way, this is assumption. Okay, all right, and this is what I have. And now I will say that the tension provided by the stirrups, right, is AV, that is cross section of the stirrups, cross section area of stirrups. Okay, and multiply Fy, which is yield strength of the stirrups. Yield strength in steel as
Bob, I think we lost you again.
Okay, let me reconnect. Okay, wait a minute. Is it back now?
Yes.
Okay, good, thanks. All right, so this AV is the each of the cross section area of the steel, okay, and Fy. All right, Fy is the yield strength of the steel, yield strength of the steel. Okay, now the game is simple, right? The game is simple, right? All I have to do is to calculate Fy and AV. I know how much contribution I have, Okay, so to do that, right? To do that, let me take an example of number 3 stirrup. So if I have a number of stirrups, number 3 stirrups, is the number 3 stirrups. Okay, the cross section area right here is AL equal to 0.22 inch squared. Okay, so AV equal to 2 legs, right? 2 legs, and that is 0.44 inch squared. Okay, then Fy for this case, usually it's 60 KSI for the yield strength, right? 60 KSI for the yield strength. Okay, but I look at the cross section here. All right, now how many stirrups I see from here? So I can count it, right? 1, 2, 3. 1, 2, 3. Right? So in terms of number, right? How do I determine that? So I take a 45 degrees of assumption. That means my crack is D. The length of the crack is D. So the length of the diagonal crack is D. Okay, so the number of stirrups is roughly equal to D over S, where S is the spacing between stirrups. Okay, so the total shear resistance of steel, right, equal to AVFYT. Okay, let me just put the T here. Okay, that's the stirrups yield strength, right? AVFYT, right? That is single stirrups contribution, right? Contribution from single stirrups. Okay, the multiply by number of stirrups, that is D over S. Okay, D over S. So this is number of stirrups. Okay, all right. So now this VS, that is the shear resistance from the steel, is determined by the cross-section area of the stirrups, which include normally two legs, right? Multiplied by the yield strength of the stirrups, and multiplied by the number of stirrups in this diagonal crack, Okay, so this is the equation for vertical stirrups. Okay, for vertical stirrups, because sometimes I may have a section with an arrangement that the stirrups is not, now this is longitudinal bar steel, and the stirrup usually is vertical, but sometimes I have inclined stirrups, meaning my stirrup sticking out like that, inclined. Okay, inclined. Okay, and still they have a spacing of S. All right, and the effective zone here still D, because it's 45 degrees. And assume the stirrups has an angle of alpha with respect to the horizontal direction, and I always forgot this is my support. Okay, what will I have, right? So in this scenario, my VS, okay, and I'll say this is inclined. Okay, this is inclined. That's equal to AVFYT still, okay, multiplied by D over S still, but multiply and correction factor, which is sine alpha, okay, sine alpha plus cosine alpha. Okay, sine alpha and cosine alpha. All right, so now summarizing. So VC is 2 lambda square root F prime C, and good question before is PSI. BW, which is the width of the web. Sorry, today's pretty dry, okay? But these are just concept, and this is the depth. Okay, that's for the concrete. And for steel, two possibilities, right? If it's a vertical stirrups, you use AVFYT multiplied by D over S. Okay, so this is vertical stirrups. Okay, or you use AVFYT multiplied by D over S multiplied by sine alpha plus cosine alpha, and this is inclined stirrups with an inclination angle of alpha. All right. So together, the total shear resistance Vn equal to Vc plus Vs. And we have to ensure that phi Vn, that is phi Vc plus Vs, has to be greater than equal than Vu. Greater than Vu. Okay. Now all these, let me just circle it out and start it. So this is the essence of shear design. In another word, these equations are only equation you need to remember for the shear design. The shear design. Okay. All right. Any good questions? I mean, any questions so far on the shear design concept? Guys, are we good here? Any questions? How we use them, you know? Any questions on the definition of each parameter of the shear? Okay, so I think this is a good point for us to stop. Today, we're just gonna show you the basic concept of the shear resistance, okay? I would like you to go back and review, okay? Go back and review what we have done on this, okay? Now, we haven't done a quiz for quite a bit. So today I'm going to leave you quiz 6, okay? And quiz 6 is due next Monday, okay? And to be more specific, I believe next Monday is the 12th. Okay, so what's the quiz about, right? So I'll give you a section. Let me just draw it down here. And I have a width of the section equal to a 12-inch. Height of the section H equal to 22 inches. And my bars, okay, are 2 number 9 bars with a number 5 stirrups. These are hanger bars, okay? These are hanger bars, so ignore the compression reinforcement, and you probably don't need it anyway. So number 5 stirrups. Okay, and concrete strength F prime C equal to 4,000 psi. Okay, now the yield strength for the stirrups FYT, let's say equal to 40 ksi. Okay, a little bit different, 40 ksi. Okay, I want you to help me calculate what is VC and what is VS if spacing of the stirrups S equal to 10 inches. Okay, all right, so this is the quiz number 6. Like I said, we have exam this week, so I don't want to burden your work. So this quiz will only be due next Monday, okay? You have time, next Monday. Okay, and you have all the weapons at your disposal to calculate this. And since it's a vertical stirrups, okay, so preferable use the equation here. Use this equation. Okay, use this equation. All right. Okay. Any questions for me? Any questions on the shear? All right. We will have our office hour tomorrow, 2 o'clock. Again, when you sign up, Zoom will automatically inform me that. So I jump in right away to discuss with you. If you miss me, send me an email and we can go over some of your questions. Now, we'll have a review session on Wednesday. We'll have a review session on Wednesday, talk about potential problems on the exam. If you haven't started reviewing process yet, I really need to start looking at it. So you have more questions coming on Wednesday, okay? All right. Other than that, if you have any other questions, welcome to stay behind. We can chat a little bit. If not, I see you on Wednesday. All right. Thanks a lot.